Hello everyone, this is Mr. McMillan, and I'm here today with the instructional notes on the laws of logic. So this is the last bit that we're doing for the laws of logic. And so when we look at the laws of logic, all we're doing is using our reasoning skills, and there's going to be two in particular that we're mostly concerned about. I'll mention a third, but the second or the first two are the ones that we really care about. Okay, so it says you may assume that the following statements are true. Read them, then answer the questions below. So our first statement is, if it is a Wimbort, then it is a glute. If it is a Zeppi, then it is a Wimbort. If it is a glute, then it has 3 eyes. So the first thing is, it says Morty is a glute. What else can we conclude about him? Well, if we look here, we're going to see if anything starts out with it being a glute, okay? So the third statement starts out with, if it is a glute, then it has 3 eyes. So if Morty is a glute, then by this statement, he must have 3 eyes. So we can conclude that Morty has 3 eyes. And that's our third statement. Okay. Now we can't conclude anything else about him other than the fact that he has 3 eyes, because if it has 3 eyes is not one of these starting points here. So all we can say is that Morty has 3 eyes. Next up, Bully is a Wimbort. Can we determine how many eyes he has? Explain your reasoning. Well, again, we're going to start out. It says Bully is a Wimbort. So we're going to see if one starts out with Bully is a Wimbort. Well, it says if it is a Wimbort, then it is a glute. So in this first statement here, we know Bully is a Wimbort, so Bully must also be a glute. So Bully is a glute. That's statement 1. Next up, if it is, so then we say it is a glute. Well, a Wimbort, then it's a glute. So do we have anything that continues on talking about being a glute? The third statement does. If it's a glute, then it has 3 eyes. So since Bully would have to be a glute as well by statement 1, that means that Bully has 3 eyes. And that is by statement 3. So yes, we could, because we figured out he was a glute by statement 1. And then since he's a glute, he has to have 3 eyes. All right, number 3, Lulu is a Zeppi. What else can we conclude about her? So the same deal is going to happen. So we're going to start out with she's a Zeppi. So the statement 2 here, it says if it is a Zeppi, then it's a Wimbort. So since Lulu is a Zeppi, we know that Lulu has to be a Wimbort as well. And that's statement 2. Okay, is there anything else we can conclude about her? Well, if Lulu is a Wimbort here, then it says it must be a glute. So Lulu is also a glute. So that would be because of statement 1. And then since Lulu is a glute, she must have 3 eyes as well. Okay. All right, number 4. It says Hatta does not have 3 eyes. So does not have 3 eyes. What can we conclude about her? Okay. Well, she does not have 3 eyes. Is there anything that mentions that she has or something about 3 eyes? Well, this third statement does. If it is a glute, then it has 3 eyes. Well, if Hatta does not have 3 eyes, could we say that she's not a glute? And the answer is yes, we could say she's not a glute. So Hadda is not a glute. That would be because of statement 3. Can we say anything else about her? Well, if she's not a glute, can she be a wimboard? No, she can't be a wimboard either because she's not a glute. And if she's not a wimboard, can she be a zeppy? And the answer is no, she can't be a zeppy either. So Hadda is not a glute. She's not a zeppy or a wimboard. So she's not a wimboard because of statement 1. And she's not a zeppy because of statement 2. So then the fifth bit here wants us to write a conditional statement that is true based on the above statements, but is not already listed. So if you remember back in algebra where you talked about the transitive property, you might have talked about the transitive properties for inequalities as well as the transitive property for equality. And if you remember, we had A equals B equals C, or sorry, if A equals B and B equals C, then that meant that A equaled C. We kind of do the exact same thing here, okay? So if you had P implies Q and then Q implies R, then we can say that P implies R is true. Basically, we're cutting out that middleman here, right? So we're taking those Q's and we're saying, hey, get out of here. We're just leaving P implies R, okay? Because there's a much simpler way to write it. So, for instance, here it says, if it is a wimboard, then it is a glute. Well, we also said that if it was a glute, then it has 3 eyes. So we could say that if it's a wimboard, then it has 3 eyes. That could be one of the conditional statements that is true. So if it is a wimboard, then it has 3 eyes. Okay. Well, we could have also said, for instance, we said if it is a zeppy, then it's a wimboard. Well, we said if it's a wimboard, it's glute. And then we said if it's a glute, it has 3 eyes. So we could say the same thing about the zeppies. If it is a zeppy, then it has 3 eyes. And so on and so forth. There are a bunch of different ones that you could do just based on following those along. And I'm going to tell you, we just used the laws of logic. So if you've been, answering along as we go along, you just use the laws of logic. Congratulations. Okay. There are 3 laws of logic that we are going to talk about and mention. The first 2, the law of detachment and the law of syllogism, are the ones we're going to focus on. And the law of contrapositive is important, but that's not a focus for what we need to know in this class. Okay. I will show it to you so you know about it, but overall it's not something that we need to know. So let's move on to the next page here where we define what the law of detachment, syllogism, and contrapositive are. All right. So if we're talking about the law of detachment, the law of detachment states that given a true conditional statement, if the hypothesis of the conditional statement is true, then the conclusion is also true. Okay? So if the hypothesis of the conditional statement is true, then the conclusion is also true. Symbolically, this is what you're going to have. P implies Q is true. And it says if the hypothesis is true. So the hypothesis here would be P. So P is true. Therefore, and the symbol we use for therefore is just 3 dots in a triangle. Therefore, we say the conclusion is true, and in this case, Q is our conclusion. So the big thing about the law of detachment is that when you write this out in column format, we're going to write this out here. P implies Q, P, therefore Q. The law of detachment only works in the forward direction. Okay? It only works in the forward direction. It doesn't work backwards. So you can think of this like the scientific method, right? When the first step when you make a experiment or whatever else, you want to make a guess of what causes something or what is affecting something, right? And that was your hypothesis. So the hypothesis always came first, and then you went through and you did all your experimentation and everything else, and then you determined your conclusion. Now, based on your conclusion, does your conclusion always say that your hypothesis is right? And the answer is no, right? So you could have a correct conclusion, but be completely wrong about why you got there, right? So you could have the correct conclusion, but your hypothesis be completely off. That's why this doesn't work backwards, okay? Because it's just like a science experiment. So instead, what you're doing is you're working forwards, okay? Basically, you're detaching the conclusion after you've said that the that the hypothesis is true, okay? So this only works forward. It does not work backwards, okay? So whatever is here has to match up with whatever's here. So these two have to match. And it doesn't matter what they are. They could be not R, Q, S, whatever it is. They're just letters. Those two must match in order to conclude that your conclusion is true. So, for an example, what can you conclude from the true statements below? If you wash the cotton t-shirt in hot water, then it will shrink. Then your second statement is you wash the cotton t-shirt in hot water. So what do you think would be your conclusion? Well, just thinking logically about it, if I wash the cotton t-shirt in hot water, then by this statement, it's going to shrink, right? So your conclusion would be, therefore, the cotton t-shirt will shrink. Now, I want to show you how to write this using the symbolic notation, because a lot of times the symbolic notation does help out. So it says, if you wash the cotton t-shirt in hot water, then it will shrink. So remember, the words that follow if are your hypothesis. So from here, from you all the way to water, so you wash the cotton t-shirt in hot water, we're going to say that's P. And then this says, then it will shrink. So this is Q. So we have P implies Q. And then it says, you wash the cotton t-shirt in hot water. Now, this sentence lines up with P. It's the exact same. So we got P here. And since we have P implies Q and P, the first two here match. So these match. So that means we can indeed conclude that Q is true. And that's what we did, right? Therefore, the cotton t-shirt will shrink, because that's what Q stands for. Q is it will shrink. Okay? So sometimes it will help, well, most times it will help if you put it in column notation form and then go from there. Okay? Just make sure you pay attention to the wording of your statements. All right, next up is the law of syllogism. The law of syllogism says that you're given two true conditional statements, and these are if statement P, then statement Q, if statement Q, then statement R, then if statement P, then statement R must be true. So symbolically, P implies Q is true, Q implies R is true, therefore P implies R is true. And the reason this works, if you want to think about it in a more algebraic way, is you have P implies Q, Q implies R. Okay? This is kind of using that transitive property we talked about, right? So if you have P implies Q and then Q implies R, you can cut out that middleman and you say that P implies R. The way I like to think about it is that for this to be valid, the diagonals have to match. And it doesn't matter which diagonal matches, whether it's this diagonal here or this diagonal here. But here, we see that the Q's match. So those cancel each other out. And on the left side, you're left with P. And then on the right side of the arrow, you're left with R. So therefore, P implies R is true. So let's look at this. What can you conclude from the true statements below? If it snows today, then I will wear my gloves. If I wear my gloves, my fingers will get itchy. Now, since we have two if-then statements, our conclusion is going to have to be an if-then statement. Okay? So I'm going to go ahead and put this in symbolic form. So if it snows today, so it snows today, that's the first statement, so we're going to put it with a P. Then I will wear my gloves. So I will wear my gloves, we're going to put that with Q because it's different from it snows today. Then it says if I wear my gloves, so that's the same thing as Q, so we're going to label that with Q again. And then my fingers will get itchy. Well, that doesn't match up with either P or Q, so this is R. Okay. So what we want here is to write this out in column notation, and we get P implies Q, and Q implies R. So we're looking for the diagonals to match. Do the diagonals match in this case? Yes, they do. We see that the two Q's match up on the diagonal, so we're going to cross those out. And we can say that therefore, P implies R is true because P just drops down and R just drops down. Okay? So therefore, and now I'm just going to translate the symbolic stuff back to English sentences. So therefore, if P, so it snows today, then, and it says R, which is my fingers will get itchy. Okay. So I strongly recommend whenever you have English sentences to put them in symbolic notation to figure out if your diagonals match a little bit easier. Now you can see that just by looking at the sentences and then just drop everything down. Okay. Some problems will only be symbolic, so you need to make sure that you understand that the diagonals have to match even in the symbolic form. All right, and the last law, which we're just going to glance kind of over, is the law of contrapositive, which states if a given conditional statement is true, then the contrapositive of the conditional statement is also true. So symbolically, if you have P implies Q is true, therefore, not Q implies not P is true. So if you have your original statement and your contrapositive are both true. And this leads to something that is very unique as far as this goes. If you remember, the law of detachment only works in the forward direction. Well, the funny thing is about the law of contrapositive is it only works in the reverse direction. Okay, and by that what I mean is if you have P implies Q, and then you have the negation of Q, you can say that the negation of P is true. Okay, so this works backwards. But again, we're only glancing over this, so it's not the biggest deal in the world. So consider the following true statement. If the team wins the semifinal, then the team will play in the championship game. What can you conclude from this true statement? Well, you know that the contrapositive has to be true. So you say, therefore, if the team does not play in the championship game, then the team did not win the semifinal. Okay. So that's all the law of contrapositive states. But our main focus is going to be on the law of detachment and the law of syllogism. Okay. All right. So let's look at some example problems. There's 10 problems here that we're going to go through. You can try these as we go along, to see how well you're doing with them. So read each argument in the problems below. Are the conclusions valid based on the law of detachment? So it's asking about the law of detachment. So the law of detachment only has one conditional, and it has just a statement by itself. So it doesn't have two if-then statements. So let's look at number one. Number 1 and 2, it gives us completely in symbols. So what we're going to do is put it in column notation. So the first statement it gives us is not P implies Q. And then the second statement it gives us is not P. And then it says our conclusion is therefore Q. Our job is to see if that's valid based on the law of detachment. Now remember, the law of detachment only goes forward. So we need our hypothesis to be true to conclude that our conclusion is true. So let's look. So we've got not P implies Q. Our hypothesis is not P. Well, in our next statement, it says that not P is true. So is our hypothesis true? Well, these two match. These match. So we're good on that front. And can we conclude then that since the hypothesis is true, that the conclusion is true? Well, by the law of detachment, yes, we can. So this would be valid. All right. Next up, we have not U implies not R. And then we have not R, therefore not U. Again, we're looking to see if it's valid based on the law of detachment. The law of detachment only works in the forward direction. So our hypothesis has to be the one that is correct. And in this case, we see that not R is true, which is our conclusion. So this does not work backwards. So this is invalid. Okay, it only works forward, not backwards. All right, so number 3, it says, if it is snowing, then I grab my boots on the way out in the morning. I grabbed my boots on the way out this morning. Therefore, it is snowing. So let's look. We're going to translate these sentences into symbols and then see if it works. So it is snowing, we're going to say is P because it's our first statement. Then I grab my boots on the way out in the morning will be Q. Here it says I grabbed my boots on the way out this morning again, so that's Q again. Therefore, it is snowing. So therefore, P. So here's the way that it writes out. P implies Q, then Q, therefore P. So by the law of detachment, we need our conclusion, or our hypothesis, excuse me, to be true to say that our conclusion is true. It only works forward, not backwards. So here, is the hypothesis said to be true immediately, or is the conclusion said to be true? Well, it says the conclusion here, we can't work backwards, so this is invalid. Number 4, if it is cold outside, then I will wear a jacket when I go outside. It is cold outside, therefore I will wear a jacket when I go outside. So it is cold outside, that's P. I will wear a jacket when I go outside, that is Q. It is cold outside, well, we're going to say that's P again because it matches up perfectly with P. Therefore, I will wear a jacket when I go outside. So that would be Q because it matches up with Q. So in column notation, we have P implies Q. P, therefore Q. For the law of detachment, the hypothesis has to be true. So these first bits have to match here. So these do indeed match. The hypothesis is true. We can work forward from that and say that the conclusion is true. So this is indeed valid by the law of detachment. All right. Numbers 5 through 8, it wants us to read each argument in the problems below. Are the conclusions valid based on the law of syllogism? So let's look at 5. 5, it says, given not P implies R, and then not Q implies not P, and then it says, therefore, R implies not Q. Well, let's look at and see what we have. The law of syllogism is based on 2 or more if-then statements, okay? And then what we need to do is see if our diagonals match in order to cancel out what we need to. So let's look here. Do our diagonals match? And the answer is yes, the diagonals do match. The diagonals for the not P match, so we can cancel those out. And this leaves us with whatever is left dropping down. So then this should be, therefore, not Q implies R. But is that what the problem says? Does it say, therefore, not Q implies R, or does it say something different? Well, it says, therefore, R implies not Q, which is the converse of this, which is not the same. So this would be invalid because this conclusion doesn't match up with what it should be. If this had said, therefore, not Q implies R, we could say it's valid and move on. All right, number 6. Number 6 says, given T implies R, W implies T, R implies S, therefore W implies R. So what we're going to do, since we have 3 here, we're going to start with our conclusion here and see if there's something that works out. So is there a path where W can go to R with shared middlemans? And the answer is yes. You start with W goes to T, so W implies T, and then T implies R. So if W implies T and T implies R, then W must imply R, so this would be valid. Number 7, if she does not eat meat, then she must find alternate sources of protein. If she is a vegetarian, then she does not eat meat. Therefore, if she is a vegetarian, she must find alternate sources of protein. Again, we're going to put it in symbolic form to make it a little bit easier to notice. So it says, if she does not eat meat, this would be P. Then she must find alternate sources of protein. That would be Q. Then if she is a vegetarian, well, she is a vegetarian is different from P or Q, so that will be R. Then she does not eat meat. So does not eat meat, that would be P again. Then our last statement, therefore, if she is a vegetarian, that was R, she must find alternate sources of protein, that was Q. So our argument written out here is P implies Q, R implies P, therefore R implies Q. So let's look at that and see if that's correct from our first two statements here. So from our first two statements here, our diagonals need to match. If our diagonals don't match, then we're done. We can say that it's invalid because there's no way to conclude anything. So we've got P implies Q and R implies P. Again, it doesn't matter which diagonal matches. All that matters is that one of them does. Well, we see that our P's match on the diagonal here, so we can cancel those out. And the other remaining letters drop down in their appropriate spots. So R is left on the left side and Q is on the right. And if we look at our conclusion, it says, therefore R implies Q, which is what happens when our P's cancel out there. So this would be valid. Then finally, number 8, if it is snowing outside, then school will be canceled. If it is cold outside, then it is snowing outside. Therefore, if school is canceled, then it is cold outside. So first off, it is snowing outside, we'll label as P. School will be canceled, we're going to label as Q. It is cold outside, that is different from either P or Q, so we're going to put that as R. It is snowing outside matches up with P again. Therefore, if school is canceled, that's Q. And it is cold outside, that is R again. So we end up with P implies Q, R implies P, therefore Q implies R. Again, we see that the diagonals match here, so the diagonals match on P, so these get canceled out. And on the left side, we should have R, and on the right side, we should have Q. But in this case, we have therefore Q implies R instead of R implies Q, so this would be invalid. And our last two problems here, it wants us to determine if there is a valid conclusion, and if so, to write the correct law of logic. So the easiest way to do this is to do the symbolic form, and then if it is valid, translate it back into English sentences. So it says on number 9, if a tree falls in the woods, then it makes a sound. A tree falls in the woods. So what is the conclusion? Well, so we have a tree falls in the woods, that would be P. It makes a sound would be Q. And then it says here, a tree falls in the woods, that would be P. So we have P implies Q and P. Well, the law of detachment is the one that uses one if-then statement and just a single statement. And since this one has the hypothesis being true, we can work forward and say, therefore, Q is true. So our conclusion would be, therefore, it makes a sound, because that's what Q is. And our law of logic would be detachment. Number 10, if the measure of an angle is 180 degrees, then it is a straight angle. If an angle is a straight angle, then it is a line. So if the measure of an angle is 180 degrees, that's going to be P. Q will be it is a straight angle. And it says if an angle is a straight angle, so that's Q again. And it is a line would be R, because it's different from P or Q. So our statements here are P implies Q and Q implies R. So we have two if-then statements, so we need to see if the diagonals match. And if we look here, we see that the Q's match. So we can conclude that therefore P implies R. So writing that in symbols, we say therefore, if P, so P is the measure of an angle is 180 degrees, then R, and R is it is a line. And the law of logic would be syllogism. So syllogism is the one that uses two if-then statements. Detachment only uses one, and it only works in the forward direction. All right, on the worksheet, I believe I put in the instructions not to do 7, 10, 14, and 17. Do all the other ones there. We will be talking about that in class, talking about that worksheet and going over some more example problems tomorrow, just to make sure that we have everything good, because I know that the laws of logic are a bit tricky to get at first. But once you get into the flow of it and start writing everything as symbols, hopefully it becomes a bit easier there, okay? Like I said, geometry is mostly pattern-based and logic is no different. That's going to be it for this video, guys. I really appreciate you watching to the end here. I hope this video helped. And, you know, if you have any questions, please feel free to email me and let me know. Okay. Thanks, guys, and I will see you in the next video.